let's do another example of finding the list of possible rational zeros using the rational zeros theorem, and then trying to determine which ones are actually zeros within the polynomial. As it says, we're going to start with the polynomial 2x cubed plus x squared minus 13x plus 6. Again, our eventual goal is to factor this polynomial, but let's start by using the rational zeros theorem to find the possible zeros. And then it says to use a calculator to determine which of those are actually zeros. And then once we find the actual zeros, we can factor them synthetically as we did before. So again, it always starts with the leading coefficient and the constant coefficient, because those two numbers are integral in those possibilities, as I was saying in the last video. So the constant coefficient here is 6. Whoops, let me get my pen out. And the leading coefficient is 2. And we want to make sure we find all the factors. So all the factors of 6 would be plus or minus 1, 2, 3, and 6. And the factors of 2 are plus or minus 1 and 2. And basically every single number in this list divided by every single number in this list would give us the complete list of all possible zeros. So all possible zeros are within this set, which would be, well, either 1 over 1 is 1, so plus or minus 1. It could be plus or minus 1 over 2. It could be plus or minus 2 over 1, which is of course 2. It could be plus or minus 2 over 2. Notice that 2 over 2 is just equal to 1, which I already have in my list. I don't need to write a duplicated answer in a mathematical set. Then it could be plus or minus 3 over 1, which is 3. It could be plus or minus 3 over 2. It could be plus or minus 6 over 1, which is of course 6. Or plus or minus 6 over 2, which again, that is 3. I already have that in my list, so I don't need to say it again. And usually we write sets in order, but I don't want to rearrange it, so it doesn't really matter if it's not in, order from largest to smallest. But you get the picture. Anyways, basically this gives me, and I meant this to be an element of symbol, basically the epsilon, which signifies that all the zeros must be within this set. Here, we can see that we have a total of 12 possible rational zeros. So in the last example, there were only 4. Here we have a little bit more. And basically, in a polynomial where the leading coefficient and constant coefficient are larger numbers, or composite numbers, like say 10 or 100, there's going to be more and more and more possible zeros, depending on how many factors are in those numbers. And the more factors you got, it just extends the list further and further. But it does give me a starting point for determining what those zeros are. And of course, I could now guess and check randomly, but as I suggest, I could always go to a calculator to try and figure them out without needing to grind through all the math. And anyone could brute force it, and basically you would just test them at random until you found one that actually made a remainder of 0, but I prefer to work smarter than harder. And obviously, if you don't have a calculator available, then you have no option, but we do, so why not? And now looking at this, it appears as though, here it's kind of hard to see. You can always just zoom in directly upon this to try to get a better look at it. Let me actually go, say, from like negative 3.5. Just going to tweak my window a little bit so I can try to see the behavior of the zeros. And it appears as though negative 3 is a 0. Also, why the rational zeros theorem is helpful is that when I'm looking at a graph, I can sort of say, well, this looks like minus 3. How do I know if it is or not? If it's on my list, which it is, that's a good indication. Okay, well, that one could actually work. And say looking at this one, looks like it's going through 2 right there. That is also a possibility. So those I would say are most likely options. Also, looking at this one here, notice it's directly halfway between 0 and 1. And so perhaps, obviously, zeros don't have to be whole numbers every time. Sometimes you could have a fractional, like 1/2 be a 0. And again, that's a possibility as well. And so let's go ahead and check those. But basically, notice that I'm getting 3 answers from here. So we could check them, and all three of them are on my list. And the only way, well, I can know for certain that they work is by actually factoring it. Again, I would suggest by using synthetic division. So let's go ahead and do synthetically. And actually, let's start with one that I probably wouldn't do myself. I would personally probably start with either 2 or -3, because those are pretty easy. But let's give ourselves a challenge. Let's try 1/2 and see, is that actually a 0? Because so far we haven't done any examples of fractions, but you can actually do fraction, you can divide by fractions synthetically. It works out totally fine. Again, assuming it actually works, which we don't know yet. But let's try it out. So first we drop the 2, then we multiply by 1/2 is 1. 1 plus 1 is 2, multiply by 1/2 is 1. Add -12, multiply -6, 0. So what I see is that indeed 1/2 is a 0 of the polynomial, as the graph suggested. And also, what does that mean about the factorization of my original polynomial p of x? Well, x minus 1/2 is a factor of that. And what will be left over from that is 2x squared plus 2x minus 12 after all is said and done. And then, I have other zeros such as 2 and -3. We could try those as well. Let's just try -3 arbitrarily. And again, I could factor synthetically, or if you're good at factoring, you could probably just factor this using, basic algebra. But let's just do it synthetically, because why not? 2 times -3 is -6. -4 times -3 is 12, 0. And that would leave me with... So again, I'm basically using synthetic division to factor this quadratic. I factor out x plus 3, and that leaves me with 2x minus 4. And one last thing that you probably noticed about this polynomial, or also 2x minus 4, is there's a common factor. And what a more normal way of writing this, because notice how when I write a factor like this, it seems kind of strange to write a factor within a polynomial. And this isn't something that's done very often. And I'm not saying it's wrong, but it's not really a correct way of writing the final answer. And really, notice since there is a common factor of 2, how we usually do it is we would actually pull this out of this factor and move it into this one. Basically, I could factor out the common factor of 2. Usually we put that out front, because clearly 2x minus 4 had a factor of 2. I could have also pulled it out here, and it would have gotten me to the same point. And then we can redistribute 2 into the factor which has a fraction in it. So if I then applied the distributive property, that would give me 2x minus 1, x plus 3, and x minus 2. And this is the most prototypical way of writing the complete factorization of the polynomial. It's not that there's anything wrong with this way either. It's just usually, since the original polynomial had only integer coefficients, we usually like to write our factors using only integers. And that just means when I do have a fractional value within there, and notice that since there was a leading coefficient of 2, there should always be that final 2 in the completely factorized form, but I could always remultiply that 2 into the factor which had the fraction in it. So I don't mean to get too into all these little details. I just thought I'd mention, because you will run into fractions sometimes. It's obviously a possibility, because these sorts of factors are quite common in polynomials, and I just thought I'd mention how you deal with fractions as such.